Okay, so let's continue the machine learning lecture. And so we will have now a lecture. I will actually introduce finally deep neural networks and talk a bit about that and their dynamics. And then I will talk about variational inference, which is a specific method to solve statistics problems or solve inference problems in machine learning. Right, and in the second session, you can all play with Google Colab notebooks. And if you haven't done so, train your first little neural networks and play differentiable physics simulators and try to solve some simple problems. And the plan was then that I just show the notebook in the front, and you can work through the exercises. And at some point, I will ask if somebody has solutions, and we will discuss them. And we will see how it goes. Good. So today I have a few less slides here, so I think I will get through all material, I hope. So the first thing to discuss is the last thing that I couldn't get through yesterday, which is how we build artificial neural networks out of the little building blocks that we discussed yesterday, or inspired by that. And so we'll talk about what's called a multi-layer perceptron. And the basic idea is that we take the minimum building block that we had yesterday from a logistic regression. So this was the model that was taking inputs from a bunch of nodes, let's say x1, x2, x3, x4, and then combines them to a common output that, so that lives somewhere between 0 and 1. And we use this to model probabilities, right? So we could use this as a binary classification model. And the underlying model was here that we modeled the output as some to be fitted weights times basis functions which depend on the input. So this here are nonlinear transformations which are fixed and predefined by hand. So the example that I had yesterday were just the components or the terms of a second order polynomial. And this here's the sigmoid function. So it's just a function that takes numbers on the real axis and squeezes them between 0 and 1. Good, so we take this kind of model and now essentially just stack it. So the idea is, okay, we could again have a bunch of input neurons, but rather than just combining them to one output, we now combine them to, say, 4 outputs. So we would have all these connections. So the input would be mapped onto some on a larger number of intermediate neurons now. And then we can take the output and again take these 4 values and use them as inputs to a next layer of neurons. And everything will be here connected with everything in that sense. I mean, one layer is connected to the next layer in this case. So it's a feed-forward neural network where just subsequent layers are connected. And then this output could be finally, if you wanted, combine it into a single neuron, which we can then put through a sigmoid function, and then we would have suddenly a model for binary classification again, for instance. But we could also, if you want, have 2 outputs or a larger number of outputs, and simply not apply the sigmoid. So the calculation or the model that was to describe is a general mapping from some input space with dimensionality dn. So here it's just 3-dimensional input to some output space, which could be also of any dimension. So here it's 2-dimensional output. And it's useful to write this in terms of temporary variables. So the input would be x, which would correspond to some temporary variable 0. And then the next layer would have value t1. Next layer would have value t2. And then the last layer, the output layer, would be t3. Good. And now the operations that we use here, I think they will fit in here, will be simple. So they will be as simple as 0, even simpler. The input would be just x, and then the first layer would be described by some affine transformation of the input. So this means we need a matrix, a weight matrix W, W1 because it corresponds to the first layer, and some bias vector. And so in this example here, W1 would have shape 4 times 3 because it takes input vector of length 3 and turns it into a vector of length 4. So this is a 4 by 3 matrix. And OK, this here would be a pretty boring affine transformation. So we put the activation function in front, which is applied component-wise. And traditionally, this had been the sigmoid function. But there are many other options and better options for deep neural networks, which I will discuss. So, but the idea is we now repeat the same structure over and over again until the last layer, which typically wouldn't have an activation function, but it depends on what one wants to use this for. And then the output is just this, this last layer, OK? So this here would be essentially a deep neural network, multi-layer perceptron. And you see it's a combination between fine transformation and nonlinear activation functions. And so far, this model doesn't do anything particular. So if you would write the model and initialize it, you would assign random numbers to the weights and the biases in a specific way, typically so that everything within the network remains of order 1 if you plug in order 1 numbers. Yes?
What's the activation?
That's exactly what I will discuss now. So the question is now what activation function to use. And it's called activation function because it simply describes how strong the output is of a specific neuron as function of the input. So as I discussed yesterday, the kind of biologically inspired example would be just a Heaviside step function, which would either fire or not. Something inspired by this multi-layer perceptron would be actually sigmoid functions. So I write this down first. So one option would be a sigmoid function, which looks like this, right? So we had the definition yesterday. So the problem is now so this looks like a valid activation function, right? It's a nonlinear function. We can also differentiate it. One problem that occurs when now using gradient descent is that we have to calculate derivatives of, by applying the chain rule to the entire network. So at some point, we will also have to deal with the derivative of the sigmoid, which has this simple form. And so this means the maximum, so the derivative would look like this here. It's a little bump centered on 0. And it's essentially close to 0 anywhere far away from that central region. And historically, this has caused problems in training deep neural networks because this leads to diminishing gradients if you go further or deeper and deeper into the network, simply because you start multiplying more and more of these relatively small functions. And the underlying reason is not so much that the peak is very high, but the activation function is bounded. Since it's bounded in a large region of the parameter space, the gradient will be close to 0. And so this turned out to not work not very well. And no, this doesn't work well. So what instead has been used a lot, and it's the simplest option, but certainly not the only one, is what's called rectified linear unit, which has a very simple definition. It's just 0, below 0, and above 0, it's just the input. So this here would be this would be ReLU activation function. This looks very simple, right? The nice thing is now that the derivative actually doesn't vanish if you go far away from 0, at least if you go to positive values. If you go to negative values, it's 0. But yeah, since the function is not bounded, the gradient can be non-zero, also far away from the central region. Good, so this is one of the many activation functions. You can think of your own activation function and then train a neural net and see if it performs better than ReLU. But it turns out that building neural networks just based on this simple activation function works very well in many cases. So the derivative of this year's just the Heaviside step function, right? Good, and what I already mentioned is that the activation functions are applied component-wise. So if you plug in a vector, the output would be simply the activation function applied to all vector components. N, yeah. Okay. And so essentially, a deep neural network in this setup here is just a mixture between affine transformations and these activation functions. If you remove the activation functions entirely, you would just have a product of linear transformations. And if you go from 3D to 2D, all the internal parameters don't matter. This would be just equivalent to having directly a linear transformation from 3 to 2D. So such a network couldn't learn much, even although it has a lot of parameters. So the activation functions actually are quite relevant to make it make the network flexible. Good. So that's the basic idea. Now, one question might ask is why it's interesting to define something like this, right? It's just a very flexible fitting function. I think yesterday I sometimes used the parameter phi to just as shorthand for all the free parameters of the model. So here in this case, the free parameters are just the list of all the weights and biases that we have in this model, right? So 1. So typically, these models can have very large number of parameters, thousands or millions or even billions, depending on more advanced network architectures. So the first point why a construct like this is interesting is related to something that is called universal approximation theorem. It's a pretty fancy name for something relatively simple. So the idea is simply, let's consider construction like this, neural network like this, with just one input and one output and one hidden layer. So it would look like, I'll put it here, would look like this. And then this goes all together. So there's just one hidden layer. Then we can, so this would correspond to L equals 2 in that example. Then we can write this network in the following way. So we would have the weights from the output layer times the activation function, which in our case is just the ReLU, and the weights from the first layer multiplied with the input parameter plus some output. Okay, and so this is the number of hidden units that we have here in the hidden layer. And this is now just a sum over functions of this form, right? Over functions of this form. So we can use the weights and the biases essentially to determine when the function turns from 0, when it turns on, and then we can use the weights to adjust the slope of this function, whether it goes up or goes down, and whether it points in the left direction or the right direction. So what we can use this for is to build arbitrary stepwise linear functions. So that, let's suppose we want to fit something like a sine curve, right? Something that looks like this. input is x, the output is y. And now we want to tune the neural network such that it represents this sine curve. Then if we would just use one term, maybe we would have something constant here, and then it would switch on here. So we would get that part right. Then the function would get diverge. But then we add another term, which might just switch on here and get us here, and so on and so forth, right? So each time we just add another term, which helps us to slightly change the slope of the function. And then we are here. And the statement of the universal approximation theorem is now actually more general than this. So this applies for a wide range of nonlinear functions, and the situation where you sum or a very large number of them. So the statement is that in the limit of d goes to infinity, you can arbitrarily well approximate any function, given that the function is sufficiently smooth or doesn't have weird irregularities. This is a statement that is true for, or that is relevant for this neural networks where you just have one hidden layer, and it suggests it's a good idea to have a lot of neurons in the single hidden layer. But what happens in practice is that it turns out to be better for training and also for evaluation to have multiple hidden layers, each with less neurons. So that's something that one finds empirically. So this universal approximation theorem just gives you an idea of why it could work. And also explains why the output of these networks, if you use ReLU activation function, will look like a stepwise linear function. Right, so this here was the sine curve. Good, so now if we would train a network like this, the light is off now. Okay. Do I have to switch? Okay, let's switch this. Is it over here? Okay, super, thanks. Good, so typical algorithm for training such a neural net. It's very similar to the algorithm that we would use for logistic regression. I'm not trying to write some pseudocode. So input would be the training data. So as we discussed yesterday, that's typically a set of inputs and outputs. And usually if you have data that you want to use to train a neural net, you would split this up into some data that you would use for training and some data that you would use afterwards for testing whether your model works well. And it's a good idea to actually split this up in validation loss and test loss, but I keep it here simple. So the input would be the training data, and then some neural network with initialized weights, randomly chosen weights. And there are some good practices in how to do this. So the weights will be randomized. Often they are drawn from uniform distribution with like boundaries, so symmetrically around zero with boundaries that depend on the size of the layer that you have. And then we need a learning rate, gamma. And in practice, you wouldn't use one learning rate, but adaptive learning rates, and there's a lot of trickery. But at the very basic level, the algorithm would be like we now repeat the training loop by sampling like a mini batch from our training data. So let's suppose we have 1 million training examples. We might just here pick 64 or 128 or 512. And then we evaluate. And the main reason for this is that it would be impossible to do it memory-wise for all the training data at once. And the other reason is that this introduces stochasticity. So we would evaluate the loss function. Then we would evaluate the gradient of the loss function. And I haven't really said what the loss function is in this context, but it will be a function of the output of the neural net. And then we update the weights by subtracting minus the gradient times the learning rate. And we do this until it's converged. And what converged means is, again, a bit context dependent. So the typical situation would be you have your loss function, and here the steps that you take during training. And what will happen is that, so what we evaluate here is the training loss, right? So it's evaluated on training data examples. So this will typically tend to just decrease over time, not smoothly, but stochastically. But there is no specific reason why it should increase again. So usually this decrease, it can be that the decrease is quite non-mono, or that there are saddle points or that there are jumps, and if you change the learning rate, you can also again suddenly decrease again. But in general, the training loss goes down. And it's a good idea to keep also track on how the network performs on data that wasn't used for training, let's say on validation data, on the validation data here. One can do this every once in a while during training. And what one observes for that is typically that at some point, so if everything goes well, initially the validation loss will decrease together with the training loss. Doesn't have to have exactly the same dynamic, but it's similar. At some point, the validation loss will either stagnate or go up again. And again, there can be quite a few subtleties, but so this here would be the loss of the validation data. The white thing's the loss on the training data. And then one way to deal with this is to apply early stopping. So to just stop the training once you see that the network starts to lead to overfitted data, to validation loss that goes up again. Usually one only knows this a bit later, so you would keep record of the networks that you used in the past and then just go back to the point where it was best. There are other strategies how to deal with this. For instance, you can, so I'm not going into this, but that's one way to do it. And then afterwards, in order to perform, to test the performance of the network, typically what you would do is you would have even another holdout data set that one uses for testing. So this was never used for training, and it wasn't also used for validation. It is only used after you finish the network training and you want to study the performance of the network. Okay, so in the exercises that you will do here, you will just train and see what happens. So there is nothing about actually stopping early based on validation losses or anything, so we keep it quite simple. But in practice, this year is important. Right, so there are now two important aspects. One is, okay, we need here actually the gradient of the network, right, or the gradient of the loss function. For logistic regression, this was something that we could just calculate analytically for this model here. And in principle, one can also do this analytically for models like this here, because it's less linear algebra, a few activation functions. But in practice, it would be very tedious to code up all these gradients. So what one uses is programming languages that know how to auto-differentiate. And there are different ways of auto-differentiation. I will discuss here briefly backpropagation. To check the time, so maybe I will skip backpropagation. And then another aspect is also, it's kind of weird that these models, okay, typically these models have so many parameters that they can easily overfit data. So you're often in the regime where fitting the model actually leads to worse validation loss at some point again. So one question is why these models can be interesting. So traditionally, you would use less degrees of freedom than you have, for instance, data points. If you make a simple fit to a curve, let's say 10 data points, you would not try to fit 10 data points with a model that has 10 degrees of freedom. Then you end up with just overfitting your model and a bad generalization. What happens in the context of neural networks is that there seems to be a new regime entering when you completely overparameterize your data, which leads to regularization and good results. So that's something I could also discuss about, but maybe not today. But maybe there will be time tomorrow on Friday. All right, another point that I wanted to make is, that's maybe interesting because it's easy to make. right now. When we use gradient descent in this way, I'll make it here. When we use gradient descent, so let's suppose we have a loss surface that looks like this. Right, so this is our loss function as function of phi, and phi is 1,000 dimensions, but I just show one here. So it might be that there are multiple minima in the sense that if you train the network once, you might end up here. If you train it another time, there's other randomness plays a role in how you initialize the weights and also what happens exactly during training. So in general, you will just end in another minimum of the loss function. Now and you might the naive intuition is now, okay, so you might be stuck in a local minimum, right? Because we just used the simple gradient descent algorithm. So how can we be sure that there's a global minimum which we reached? But there is interesting work that actually shows that all these minima seem to be connected. I'm not 100% sure that this is 100% general, but I added some papers about this to the Google Drive. So this goes back a couple of years already. So the logic is that the loss, if you actually look at the loss surface in high dimensions, so let's say like this, then there's typically a way that connects different minima that you found in different training rounds, such that you don't have to go over any hill in the loss function. So instead of thinking about the loss function as something where you have like one unique global minimum, it seems like there's a landscape or like complex valley of valid solutions that are all connected. Good. So let me check the time. Yeah, we have time for backpropagation. Good, so how do we actually train these models? Or how do we know the gradients? Good, so one thing we have to do is calculate gradients, right? And in the end, if you just write a neural net and train it, you don't have to deal much with gradients because it all happens under the hood. You don't actually see how this, you don't necessarily have to deal with how this works. But it's good to know how it works. So example, very simple example might be we have a calculation that looks like this. So it's like a sequence of operations. So we have input W0. And then we apply function h to W0 and function g to the output of function h and function f to the output of function g. And we are interested now in how y depends on the input x, okay? And of course, we would just apply the chain rule to calculate this. But one can also do this. So the way this works automatically when we do backpropagation, reverse mode backpropagation, as we build up the gradients sequentially. And so for this, it's useful to look at the gradients of y with respect to all the intermediate results. So I will define the intermediate results in a second. So we have the input W0. This is mapped via function h on W1. And then this goes to W2. And this goes to W3, which is our output. And this would be function g and function f. Okay, so this is just the computation that we are doing. Now, if we wanted to calculate the gradients with respect to of y with respect to x, we can do this sequentially. So first is we can calculate the gradient of y with respect to W1. That's just 1, right? Because they are the same. Then if we want to calculate the gradient of y with respect to W2, we apply the chain rule. So we use the gradient of the output of f with respect, or y, the gradient of y with respect to the output of f. So this is W3. That's just W3 bar, times the derivative of f with respect to its input, W2. And you see for this, in order to calculate this number here, we need actually already the value of W2, and we need the gradient the derivative of the function f. And we need to know the gradients that we had here, so the gradient of output of the network with respect to W3. So now we can go a step higher and calculate the gradient of the output of the network with respect to W1. That's just given by the gradient of the output with respect to the output of G times the derivative of G at its input. And then we can also calculate the final gradient by multiplying the gradient of y with respect to W1 with the derivative of h at W0. Sorry, this is now a bit squashed here. And now we have the gradient of the input of y with respect to x, right? We arrived at W0 bar. And in order to evaluate it, so the way in which this works practically is, if you write a neural net and evaluate it, there will be a forward pass that first goes from the input all the way to the output. And in the process, one calculates all the intermediate and stores all the intermediate values for W0, W1, W2. And then internally, next to each parameter, there are buffers for the gradient. And then if you run backprop, what happens is the computational path will be traversed like in backward in a reversed way. And the gradient buffers are populated, basically by using this recursive relation, which essentially relies on the fact that the derivative of the output with respect to any of the intermediate results can be, or with respect to any of the inputs of the intermediate operations can be expressed as the derivative of the output of the network with respect to the output of that operation, and then the derivative of the operation itself. Okay, now this is a very simple computational graph. One could now write this for more complex graphs also where you have branching and so on and so forth. And there can be situations where actually, for instance, x matters at multiple points, right? So the graph doesn't have to be like this. It can be that there are branching points that come together. So one example, which I'm not fully writing down, but you can find this in lecture notes, is f. So how is this defined here actually? F equals okay, x1 times x2 plus the sine of x1. So you find this in the lecture notes. So here in this case, x2 enters in two different terms. So if one goes back through the computational graph, there will be multiple points at which a gradient buffer will actually get contributions. It's just because if you apply the chain rule to something like this, there will be multiple terms contributing to the derivative with respect to x1. Good. So for that reason, the buffers are usually not overwritten when you run backprop, but you just add to what's already in the buffers. As a result, when finishing with the calculation, usually you have to set buffers to 0 again. So 0 gradient buffers. Which you see when you look at the code example. So there's one line that just sets all the gradient buffers again to 0. Okay, so that's backpropagation in a nutshell. There's also forward mode auto-differentiation, which doesn't work like which also uses a recursive relation to calculate gradients, but it runs from the beginning to the end, and the main difference is performance. So if you have something where you have a computation with a lot of inputs and a single output parameter, that's for us the case because we have a neural network with maybe thousands or millions of weights and a single loss function, and reverse mode auto-differentiation is more efficient. If you are in a situation where you have, if you input parameters and a lot of output parameters, forward mode auto-differentiation is more efficient. Good. So that's deep learning in a nutshell. I would say. So next thing I wanted to discuss is how to use this for solving statistics problems. But before I go there, are there any questions about this? Any questions? I at least would like to understand whether there are no questions because it's crystal clear or whether there are no questions because it's completely confusing. And probably there is a spectrum. But ask any random question or say, OK, go on, please. Yeah.
So this is actually taking it a bit back.
Mm-hmm.
So when you explained like the gradient thing, and you said that it's a problem if it peaks around 0, I'm not sure I fully understand why this is involved.
This story here?
Yes.
So a way to see this is if you would do like a sequential calculation like here, and calculate the gradient of the output of the network with respect to some weights that are very much in the beginning, then we would apply the chain rule and over calculate the multiply gradients of the sigmoid. Mm-hmm. And the maximum value of the sigmoid is 1/4. So each time you accumulate a factor 1/4, at least. And usually it's worse because this only happens when the input to the sigmoid is actually close to 0. So now one could think, OK, maybe we just squeeze the sigmoid, then the peak here becomes higher, but then it's not easy to, or not possible to trick around in that way, because you would have also to basically redefine the weights that would counter the effect. But the main problem is you accumulate a lot of factors of 1/4 in this case. And if you calculate then the gradients, so there's a nice plot that one can make. If one calculates for randomly initialized network, the gradient, how the loss function changes with respect to the weights in the individual layers, then for layers that are very, I hope I get this now right, that are very late in the network, so close to the output, the distribution will be relatively wide, which is nice, so the gradients are large. But if you then go further up in the network, the distributions will look more peak towards the center. So you suddenly have the effect that if you start training the network just based on the gradients, weights later stages of the network get more trained than in early stages of the network. And this makes it inefficient to train a deep neural network. So introducing ReLU activation functions has been a big step forward there. If you go back to like 12 years or something, look at machine learning books, they still say, OK, deep learning, great, but seems to not really work. So I think maybe 15 years now. And it's partially related to these kind of problems. And they were solved by ReLU activation functions, by skip connections, by all kinds of tricks. But often, yeah, the learning dynamics in this sense plays a big role to make this work in practice. More random questions. Yeah.
So is there any tests we can do to make sure that our training data and our validation data are statistically different? Does that interfere on the?
So in almost, I think, all cases, you would assume that the training data, I mean, all the data that you have available is independently identically distributed according to some underlying distribution. So if you just then randomly subsample, you're supposed to have independent samples. That's an assumption. Yeah. Yeah.
Next one question. So the backpropagation is something I do to just gain a better understanding of what's going on in my network. Right?
The backpropagation is because we need this gradient here for the loss function. So in order to evaluate this without actually writing down the gradients by hand, backpropagation is important. About 5 or 6 years ago, I was like optimizing huge models without knowing about backpropagation. And it was not a lot of fun to calculate all the gradients by hand and making sure that there are no bugs in the code and so on. So this kind of auto-differentiation is very useful for training networks, but it can be also useful, for instance, if you want to derive equations of motions without calculating derivatives of Hamiltonians or stuff like this. So it has many use cases. Yeah.
Are there any conditions on what can be an activation function?
Usually the logic is whatever works is great. And okay. So the question was, is there any logic or are there any rules behind what activation function to pick? I think the main decision criterion is that it works and works well. And there are a lot of variations around this simple ReLU. So you could have a ReLU where it's called leaky ReLU, where actually also you have something non-zero on the left-hand side, or there are all kinds of smooth versions of this. And in the end, this falls into this category of hyperparameter scans, or things that one has to just explore empirically and see what works better and what not. The main, I think, criterion is that it shouldn't be a bounded function. If it's bounded, then you have, again, this vanishing gradient problem. Or probably there are also counterexamples for that, but having these non-bounded functions helps a lot. OK, so let me go on and talk a bit about statistics. So for up to now, the thing that I introduced, the multilayer perceptron, is just a flexible fitting function, right? From some high-dimensional space to some other high-dimensional space. And depending on how you train it, it can turn into all kinds of things. So what I want to discuss here is how to turn this into something that we can use to perform Bayesian inference. And I will here focus on likelihood-based inference. And the plan was to focus tomorrow and on Friday on what's called simulation-based inference. And you will understand in the process what I actually mean with that and what's the difference. But to start with, so in both cases, there are classical analogs to the algorithms. And for likelihood-based inference, the starting point, the right starting point to think about, this is just regular chi-square fits, which you have all probably done in lab courses or in any kinds of contexts. So the idea is, OK, let's say we have a few data points, right, like this here, with error bars, or the same error bars. Then we can try to fit a function through this, which might look like this. So the data points have indices. And we can write down a chi-square function, which would be just the sum over all the data points. And then data minus model prediction. The model prediction will depend on some parameters. And then we have sigma squared. That's the variance of the measurement. So sigma is just the measurement uncertainty. And the underlying idea is here that the data is essentially drawn from this model, or it's centered around that model with a measurement noise of sigma. OK. So now an interesting aspect of this is that this, and I'm sure you have all done this in the past, right? Yep.
What's the sigma here?
The sigma, OK, this is the measurement noise. Yeah, so this sigma is a bit overloaded. So
Each one of these ones. Each one of them has an input.
if each one has different noise, then there would be index I. Yeah. Good. So now this chi-square, which you all know, is related simply to the up to a constant. It's just the same as -2 log likelihoods. Okay, so if you have a Gaussian likelihood function with mean values mu and like diagonal noise covariance matrix with these diagonal elements, we wouldn't end up with this chi-square function. Good. So that's something you all are familiar with, I suppose. So now what we could do this, for instance, or one thing that we could use this for is now if we are frequentists, we could just minimize the chi-square. What we would end up with then is a maximum likelihood estimator, right? So minimum chi-square is maximum likelihood. If we are Bayesians, maybe we want to introduce a prior. And we could be interested in the map estimator. So that's the maximum of the posterior. And that's what I'm going to describe here. And this would be simply given by maximizing the log likelihood plus the prior term, okay? And the reason why this is enough is because, thanks to Bayes' theorem, this here is simply the posterior plus the data likelihood. And the second term doesn't depend on the parameter that we optimize, that we maximize, so we can as well write it like this here. So the reason why I write it like this is because we will next introduce an algorithm that will eventually lead to a loss or an optimization target that will look very similar. But instead of just getting one number, right, the map estimator, which, so if this is the posterior, given the data, so that it would be just this number here. Map estimate, set map. We want to define an algorithm that actually gives us as optimization target the full posterior, and is to have some function that we optimize and that in the end ends up actually fitting the posterior of this model. Good, so in order to do that, we have to introduce a bit of information theoretical concepts in some sense, but I will keep it quite minimal. And I will talk about the Kullback-Leibler divergence. Who has heard about Kullback-Leibler divergence before? A few of you. Okay, so we want to define a fitting problem, okay? So we want to somehow have an optimization problem where instead of optimizing just a single parameter, we want to actually optimize a probability distribution too. And the optimization target is, in the end, it should be the posterior that we are interested in. So in order to define something like this, we need to have a way to evaluate how far we are off, right? So we need a loss function that tells us how different my optimization, Q is from P. And the Kullback-Leibler divergence is maybe the most prominent and well-known and popular version of it. It's by far not the only one, but it's omnipresent in machine learning. And so I first write it down. So the KL divergence compares two probability densities. And it's defined as average over draws from the first, from Q. And then we average over the log ratio of the probability densities, okay? So what you see here immediately is if Q equals P, the log is 0, and you just get 0 back. So that's good. This means that if Q equals P almost everywhere, then the KL divergence is 0. What's equally important is that one can also show that it's non-negative. And I don't have tons of. Okay, let me first. Yeah.
It may be worth saying for people who have heard of this is also called the relative entropy.
It's also called the, okay.
And in information theory, people who know quantum information, they may have heard it from that.
Yeah, so one can also write this as cross entropy of Q and P minus the entropy, for instance. So it's related to these concepts. Entropy essentially measures how uncertain the function is. So if it's very peaked, it's small entropy. And cross entropy, yeah, okay, I don't. Yeah, we can describe discuss this.
Cross entropy. I said that the relative entropy is exactly the same thing as the Kullback-Leibler divergence.
Okay, Yeah, I'm not familiar with the concept of relative entropy, but I guess it's the relation between these two. Yeah. So one consequence is that the cost entropy of P and Q, if it's the same, it's just the entropy of Q. Good. So for whom are these entropy concepts more familiar than KL? Okay. So maybe next time I should start with this. Okay, so one can show that if Q equals P, it's 0. One can also show easily using the fact that A minus 1 is always larger than ln of A. Sorry. That it's non-negative. An important ingredient in that proof is that both Q and P are valid probability distribution functions. So in that kind of proof, one uses that they are normalized to 1. If they weren't normalized to 1, first you wouldn't know how to sample from it, but if P, for instance, isn't normalized to 1, then the function is unbound, so you can get anything. Good, so let's use this as an optimization target. And now try to build an algorithm around this. And this algorithm will end up with what's called the evidence lower bound. Who has heard about evidence lower bound before? Okay. Good, so the idea is now we want to minimize the KL avergence, and we have two options. So what we want to minimize in the end is the KL avergence from Q. This will be our variational, how did I write this? Variational distribution, so the thing that we want to fit with respect to the actual posterior, okay? So the KL avergence is evidently not symmetric, so we could also swap P and Q, and then we end up with a whole different set of algorithms that solve in the end the same problem but have very different properties, and this will be simulation-based inference, which I will discuss tomorrow. But let's use this now as a starting point. So now the problem is, okay, we have this here, and we want to use this here as a loss function. But we have here ingredients that so we have here the posterior, right? So we actually don't have access to the posterior. It's not that easy to calculate the function if you don't know the posterior. So we have to massage it a bit, the expression. And to see how this goes, let me write it down explicitly. So we have here the optimization target, Q, or variational posterior, and then the actual posterior, which is intractable. And now what we can do is we apply Bayes' theorem and replace the actual posterior, formally at least, with the likelihood function times the prior. And we have also the Bayesian evidence here. So this posterior now just turns into likelihood times prior divided by evidence, okay? So we didn't know how to calculate the posterior. This was like the goal of the algorithm, right, not the input. But these are now quantities that we have a bit better under control. So typically we know what the prior is. And in this case here also we will need a model for the likelihood function. So one problem is now, however, that we typically don't know what the Bayesian evidence is, because this would require integrating over these two quantities. And that's, again, typically intractable. So what we can instead do is now realize that we can split things up a bit. So let me write this now again in terms of split up the terms into individual, well, the factors here into individual terms by just expanding the logarithm. So we would have the log of the variational distribution minus the log of the likelihood minus the log of the prior. And then what we can do is we can pull out the evidence, Bayesian evidence, because it doesn't actually depend on Z, right? So we can just pull it out, and then now it's here. And we know that this object is always larger than 0 because the KL divergence, per definition, is always non-negative, right? So now, what we can do next is to simply take this part here, which has components that we can all evaluate, and call this elbow, or actually minus elbow. And elbow stands for evidence lower bound. Stands lower bound. Simply because it's a lower bound to the evidence, right? So we know the KL divergence is always non-negative. We have now evidence or log evidence minus elbow. So if we reorder this, we get the statement elbow is always smaller than the log evidence. Yeah, so it's a lower bound to the log evidence. It's lower bound to something that we can't really calculate, but still it's a lower bound to this. So also elbow will equal the log evidence in the case where the KL divergence is 0. So where actually our variational posterior fits the true posterior perfectly. Good, so now instead of minimizing the KL divergence, our optimization goal can be to maximize the evidence lower bound. So to just take this subset of terms and maximize that. And for that, it's interesting to actually see what this means. So how the individual terms would play together. Okay, but before I go there, now have a look again at the thing that we derived from the chi-square fit, right? So here, in order to get the maximum, the map estimator, right? So the peak of the posterior, the optimization problem was we wanted to maximize this here with respect to Z, okay? Sorry, that looks a bit nonsensical. Right, so this was the optimization target. Now, if you look over there, the elbow is almost the same. We have also log likelihood, and we have the log posterior. The only additional component is now this thing here, which depends on our variational function that we want to optimize. And this will actually turn into entropy. So it's a term that favors fitting functions that have a high entropy. So that's the main difference. So instead of maximizing here a single parameter, we maximize distribution of probability distributions. And in order to make sure that they don't collapse to a delta function at the map estimator, we have this entropy term. So which counterbalances basically overfitting. Okay, so I want to visualize this a bit. So let's suppose we have now the individual components. We have a likelihood function which looks like this. So that's likelihood function. And then we might have a posterior that looks like this. A prior that looks like this. So it's a bit wider. And then we have contributions from the entropy term, from log of the variational posterior, which might look like this. Okay, and it has actually the opposite sign, but I still draw it like that. And on top of that, so these are now the contributions that we have, and we want to evaluate for this the elbow. I write this now explicitly. And there will be, again, the samples from the variational distribution, which we want to optimize. Then there's the likelihood term. And there is the prior term, and then minus the log of the variational function, of the variational posterior. And you can see this here, this part alone is now entropy. So variational entropy. This part here will be the prior, and this part here will be the likelihood function. Now, okay, when we want to optimize this, right? So the way this works would be we first have to sample a bunch of samples from the variational posterior, and they might end up, for instance, here. So these are just, let's say we have 4 samples. And now now essentially these samples want to move such that they maximize the elbow. And what want to move means I will describe in a second, but you can already see here that different components would direct the samples in different directions. So for instance, the likelihood function would like to direct the samples all to the region where they produce a good fit. The entropy term would like to pull them apart, basically, to increase the entropy. Right, so because there's a minus sign in front. And then the prior term, okay, the way I was drawing it here, it doesn't have much effect. So it would draw stuff a bit into the center, okay? And so elbow maximization essentially means practically to sample many times from the variational posterior, then calculate the gradients. It's a way that I will describe in a second, with respect to the parameters of the variational distribution. These gradients will get contributions, will receive contributions from all these functions, that from these 3 components that will direct them in different directions. And eventually, if everything works, the variational posterior should turn into something that is close to the posterior that we want to fit. Now, there's one little problem, which is once we sampled from our variational posterior, we have the samples, right? They are fixed. So if you would sample like 3 parameters, and they are like 1, 2, and 3.5 or whatever, these numbers don't depend on phi anymore. So if we just sample and then calculate the gradient with respect to phi, only this here would essentially contribute, right? So this is something that depends on phi, but these terms would drop out. So what to do? Well, it turns out that there is something that is called. So does anybody have an idea what to do? Maybe you can come up with this. And I mean, some of you will have heard about the reparametrization trick. But does anybody have an idea what to do? Oh, good. Question is, we sample here from the variational posterior, right? And we get maybe 3, 4 numbers, like these numbers here. Now these numbers don't depend on phi anymore. They are already sampled. So if you calculate afterwards the gradient of the elbow, those dependencies on the parameters have disappeared. And so if I would do it very naively, the problem would be the underlying problem is that you calculate gradients with respect to the distribution from which you sample. And once you sampled, this dependency is gone. So that's the problem that we have to solve. Maybe I just show the solution, which is not that difficult, and then you will understand maybe what the problem is. So the solution is called, for whatever reasons, reparametrization trick. It's probably not something that is like unique to this type of problem or unique of machine learning, but it's where I first encountered it. So the problem is generally how to optimize something that looks like this. So you have a distribution from which you sample, and you want to optimize now this expression with respect to parameters phi. The problem is simply once you sampled from Z, from this distribution, the samples themselves, if you do it wrongly, don't depend on phi anymore, right? And so if you calculate the gradient of this based on samples from Q, the gradient would just disappear. maybe writing it in a different, so if you write down the definition of this, right, in terms of not now Monte Carlo estimates of this expression, but the actual integral, it would look like this, right? And the problem is now if one just samples and then takes the samples fixed and calculates the gradient, that's like calculating the derivative of this object, but neglecting the part that comes from taking the derivative of this Q, of the sampling distribution. So that's the thing that we have to solve. And the strategy is quite simple. So we define we simply reparameterize our problem. So we define a function z equals, I called it h, which is a function of the weights of the network that we want to optimize. So it's a function of the fitting parameters here, and some random parameters that are just drawn, let's say, from a standard normal distribution. Okay. Now, these random parameters here are always drawn from the same distribution, from standard normal. And that's great. So there's no problem in taking derivatives with respect to those parameters because they are anyway fixed, or this underlying distribution is fixed. But then z follows from these random parameters by this expression. So we reparameterized initially normally distributed parameters such that they turn into the distribution that we want. So the logic is we define a function such that z now is effectively drawn from an underlying, from the target distribution that we want. And okay, so that might look a bit abstract, but the example is there's a very simple example. So let's imagine we have phi equal to the normal distribution with some mean value mu and some variance sigma square, right? Then the appropriate function that we would have to define, and now our model parameters are simply mu and sigma square, right? So the appropriate function that we would have to define would be simply mu plus sigma times epsilon, okay? So if we sample epsilon from the standard normal distribution, multiply it with sigma, and then add mu, we end up with random variables that follow normal distribution centered around z with variance sigma squared. Okay? And that's the reparameterization trick. And now what we can do is we can, I didn't put this, okay. We can calculate the above expression that I had there, but instead of now sampling from Q, we just sample from the standard normal distribution. And then here in the argument, we rewrite z as h times the h of phi and epsilon, okay? So now we moved the phi dependence that we initially had in the distribution that we sampled from. We removed the phi dependence from there and moved it into the object over which we average, okay? And now the problem with calculating gradients disappears because now we can just, in order to get gradient estimator, stochastic estimators for the gradients, we take that object, sample a few epsilons, plug them in here, evaluate this all, and then we can use autograd to calculate the derivative of these quantities with respect to phi, okay? So more concretely, if you have a loss function, so loss function could look like this. We have mini batches here, or batch size b, and then we would sum. No, it's not it's not a loss function. It's just this object here. So we would here, let's say, have b samples from the normal distribution, standard normal distribution with mean value 0 and variance 1. And now we use this here, right? So we rewrite this in terms of, or not, we just write here an expectation value for our loss, right? So this is now just a Monte Carlo approximation to this average here based on B samples from the standard normal distribution. And now when we calculate the gradient of this object, let me check the time, we can simply do this, right? So we apply the chain rule, so we need the gradient of f of our, we need the gradient of f with respect to z, which is now written as h. So we need that gradient, and then we also need the gradient of g of the function h with respect to the parameters that we want to optimize. And that's it. So in this way, that's the reparametrization trick. So we solved the problem of having to optimize something where we draw samples from a distribution which has parameters that we want to optimize. We solved that problem by moving that parameter dependence from the underlying sampling distribution into the function over which we average. And now we can calculate gradients and unbiased gradient estimators and optimize targets like this here. So one price that one has to pay in the context, as you can see here, is that one actually now has to calculate derivatives of the optimization target. So we need here, up there is no derivative appearing of f of z, right? The derivative, if you calculate derivatives of this object with respect to phi, this only would affect q of phi. So it's not immediately clear why this why we would need derivatives of f. But what you see here is if you apply the reparametrization trick, we suddenly need derivatives of f, right? And this means also if you want to now optimize the elbow, we actually need to be able to calculate derivatives of the likelihood function with respect to the input parameter z, and also of the prior. And that's not always there. So if one wants to use this strategy, one needs physical simulation models or models for the likelihood function, which are actually differentiable with respect to inputs. I just write down the algorithm now, the final version of the algorithm to optimize this, and then we are done.
Two minutes left.
Okay, so what about, I write this up at the beginning of the tutorial, or I write it up now in the break, and then we discuss it at the beginning. So 2 minutes for questions.
So it would matter if I change the parameterization, or I suppose that it would have the same minimum, right?
So the performance of these type of algorithms depends a lot on how you parameterize Q. So there are many ways typically to parameterize Q in practice, which all solve the underlying problem. So they all apply the reparametrization trick, but in the end, whether it works or not depends on how you do it in practice. So you might end up with different solutions depending on what you are doing.
I thought that minimum will be the same.
The minimum will be the same, but so imagine the posterior looks like this, right? So it has a huge tail. But you decide to parameterize this here as a normal distribution, right? Then the fitting function will have to figure out like how to minimize the KL divergence without being actually able to solve the full problem, right? So you will get suboptimal solutions. So, and depending on how one parameterizes this variational function, you can be in situations where you describe the posterior very well or not very well.
A simple question. I assume that we knew the prior.
Yeah.
So why do you have to minimize?
Why it appears here?
Yeah, I mean, I can just like neglect it, right? If I know the prior, why should I enter it?
The prior appears here because we want to estimate the posterior, and the posterior depends on the prior.
Yeah, but I was assuming that I may choose a prior.
Yeah.
So the minimization shouldn't depend on that.
Yeah, but I mean, in order to the minimization goal is the posterior, right? And the posterior depends on the likelihood function and the prior somehow. So they must both appear in the optimization target.
So P includes phi, the parameters.
P doesn't include the parameters. So only the function that we fit includes the parameters. So this entire thing here, let's say this here is your, this would be a concrete physics simulator, right? So a simulation model, let's say of the cosmic microwave background. This would be cosmological parameters. then x0 would be the observation of a power spectrum. So, and this would be the likelihood function for observing specific power spectra. And this here would be the priors for your cosmological model. Then you need all these ingredients to actually get a good fit to the posterior, because you need the likelihood and the prior. You also need a cosmology code that is differentiable, because you need to calculate gradients. And you need a way to calculate the entropy of the function that you optimize. So these are the ingredients that go into this. Right, but I will discuss this a bit more after the break, and then actually in the notebooks there's code where you can optimize your own elbows, and you will understand maybe a bit more how this looks in practice. And you can connect all these things to actual code pieces. One more question. I mean, this is just an example. So you can, and I wanted to discuss, maybe I will do this tomorrow, what's called normalizing flows. So these are ways to define very, very flexible fitting functions based on applying over and over simple operations to underlying base distribution, which might be, again, a normal distribution, but such that you can still calculate the entropy and that it's invertible and so on and so forth. And applications of this are, okay, variational inference like this here, but